The next type of limit that we need to evaluate is when we have a limit where the function has a hole. And just remember from our first lesson that the limit of a function at a hole always exists. So we should not get like a statement that the limit is non-existent because the limit will exist. We often refer to holes as removable discontinuities because if we can algebraically remove the hole or remove the discontinuity, we can basically write the function as a similar function. It's going to behave like the original function, but the difference is that it does not have a hole in it anymore. So they're not exactly the same functions once we remove the hole, but otherwise they will behave the same way. So there are three main ways, I guess 4 ways, but there's a few ways that we can remove a hole algebraically. One of the methods usually involves factoring. Another method involves using a conjugate. We might have to clear complex fractions, so eliminate complex fractions. And then finally, there are 2 fundamental trig limits that we're going to learn about that could also be helpful. So let's just look at this first example. And anytime we're evaluating a limit, we always want to try first to plug in that function value. So if I look at this function and if I try to plug in x equals 2, I could think of what would happen. My numerator would become 2 squared minus 6 plus 2. So 6 minus 6. So we know our numerator is going to become 0. And our denominator, 2 squared minus 4. So 4 minus 4, which is also 0. And we know that when we see 0 over 0, as opposed to a vertical asymptote, which is a number over 0, and we'll talk about those in the next lesson, 0 over 0 indicates that this function has a hole. So when we try to use one of these different strategies, if I just kind of need to look at the structure of the function to determine which is most appropriate. So looking at this looks like something factorable. So I'm going to factor this, and we want to be really careful with our notation here. I'm going to rewrite the limit notation each time. So our limit as x approaches 2, I'm going to go ahead and write this in factored form. So let's see, our numerator becomes x minus 2 times x minus 1. Our denominator, we could factor that like a difference of squares. So x minus 2 times x plus 2. Okay, so now when we look at this, we just rewrote our function in factored form, or the numerator and denominator in factored form. Now I can see that there are common factors in the numerator and the denominator. And so we just want to be careful. When we link this with an equal sign, we need to continue to use that limit notation. Otherwise, we are making a incorrect statement. So by when we remove this discontinuity with factoring, it's really the process of being able to cancel, so to speak, those 2 factors that will remove the hole. So we had a hole when x equals 2. All right, so now when we remove the common factors from the numerator and denominator, the similar function that we're working with is x minus 1 divided by x plus 2. And this should behave like our original function. It just doesn't have a hole when x equals 2. All right, so now if we plug in our 2, we get 2 minus 1 on top, 2 plus 2 on bottom, and this reduces to 1/4. All right, so if something looks factorable, chances are factoring is the method we want to use. All right, let's look at the next example. So again, when I go to evaluate this limit, I'm substituting 5 for x, and as I check my numerator, 2 minus the square root of 5 minus 1 is 2 minus 2. So that becomes 0. 5 minus 5 is 0. So again, that's how I know that there's a hole. If I don't plug in the 5, I'm not going to know that there's a hole. All right, so if I look at this, this doesn't seem like something I've ever factored before. So factoring is probably not the strategy that I'm going to use here. What we can do, though, is use a conjugate. So just a quick reminder, if you forgot what the word conjugate means, if I have two terms, let's say A plus B, if I have like the sum of two terms, the conjugate of that would be the difference of the two terms, A minus B. And we'll see how using a conjugate here is helpful. All right, so we want to evaluate this limit, but we are going to multiply by the conjugate of the numerator. So we're going to multiply the numerator and the denominator by the conjugate of the numerator. And the reason we're doing this is this will allow us to eliminate the whole, but it will also allow us to get rid of that square root in our numerator. All right, so we've created a, well, it's not really a new function. We're just multiplying by 1, I suppose. But this is equivalent to what we started with. So if I think about it, and those parentheses I wrote aren't really necessary. Grouping is implied when we have a fraction. Sometimes it just helps my brain when I'm distributing. When we look at this, when we distribute the two terms on top to each other, well, 2 times 2, I know that that's going to give me a 4. So I'm going to go ahead and actually write out my limit notation first. I know it's very tedious. So 2 times 2, that's going to give me 4. And then the reason the conjugate is helpful is this. When we multiply the outer terms, I would get positive 2 times the square root of x minus 1. But when I multiply my inner terms, I have a negative out front. So I get negative 2 times the square root of x minus 1. And when I combine those like terms, those things undo each other. They're opposites. They cancel out, so to speak. So I don't need to worry about them. I'm not going to write that out, multiplying the outer and inner terms, because we're multiplying by the conjugate. They're going to cancel out. And again, it's just to take it back to an easier example. It's like if I multiplied x plus 3 times x minus 3, I get a difference of squares, x squared minus 9, because the negative 3x and the positive 3x become 0x. So it's the same idea, it's just a little more complicated. All right, so finally, I need to finish the numerator. We multiplied the first terms, the outer, the inner. So when we multiply these last terms, the last term in each factor, I should say, I'm multiplying a negative and a positive. So I know I'm going to get a negative product. And the square root of x minus 1 times itself is just x minus 1. Now we need to be careful with parentheses because it's the entire x minus 1 that's being subtracted from the 4. So it would be incorrect to fail to put parentheses around that. Okay, so in the denominator, I'm going to encourage you not to distribute. Nothing good is going to come from that. So I'm going to leave x minus 5 and 2 plus the square root of x minus 1 as two factors in the denominator. All right, so when we simplify our numerator, I know writing this limit notation is tedious, but it is good practice. When we simplify this numerator, 4 minus the quantity x minus 1 is the same as 4 minus x plus 1, and that's the same as 5 minus x. Okay, so instead of writing that, because again, I'm looking for two factors, a factor from the numerator and the denominator, to be able to cancel out. So I see 5 minus x in my numerator, x minus 5 in my denominator. I need to factor out like a negative 1. So what if I wrote this as like negative 1 times x minus 5? Because now we can cancel, so to speak, the 2x minus 5 factors. All right, so now we are finally ready to reevaluate this limit. I'm just going to continue my equal sign down here. So our numerator is negative 1. our denominator is just 2 plus the square root of x minus 1. So now when we plug in the 5, I know 5 minus 1 is 4. The square root of 4 is 2. I get negative 1/4. All right, so I know it's a lot of work, but we just have to practice that. So going back, we said our first method that we used was like factoring. And as a math teacher, I kind of hate to use the word cancel, but I feel like you know what I mean when I say cancel, that the factors of x, that factor of x minus 2 divided by x minus 2 just becomes 1. And that kind of, makes the x minus 2 unnecessary. We said the second strategy we used was to use a conjugate. And when we use the conjugate, again, the important part, the thing that removes the whole, is when we are able to quote unquote cancel a factor from the top and the bottom. Because remember, our whole was at x equals 5, and we got rid of the factor of x minus 5 in the denominator. All right, one more algebraic strategy, and that's going to be to clear complex fractions. So again, when I look at this next example, it doesn't look like something that I could easily factor, and I don't see a need for a conjugate. Normally, when we multiply by a conjugate, it often means we're trying to get rid of a radical expression like we had in the middle example. So here's where we could get rid of the fractions in the numerator to help us out. But going back to how we should always start evaluating a limit, we should always make first sure that we're plugging in the 2. So as I plug in 2 to the numerator, if I just kind of do it mentally, 2 divided by 4 is 1/2, so I get 1/2 minus 1/2, which is 0, and my denominator, 2 minus 2, is 0. So again, we know it's a whole because we get 0 over 0. All right, let's see what it looks like to... I hope this green isn't too light. I hope it shows up. Let's see what it looks like to clear a complex fraction. There's a lot of ways we could do this. I'm going to offer what I think is the easiest method. If I'm trying to get rid of both denominators in my numerator, I'm trying to get rid of the 4 and the 2. What would help me to do this efficiently would be to multiply my numerator by the least common multiple of 4 and 2. And their least common multiple is 4. And of course, whatever I do to my numerator, I have to do to my denominator as well. All right, so just like before, I'm going to distribute the 4 in the numerator. I'm going to hold off on distributing in the denominator. Sometimes we don't need to. Like sometimes things work out nicely. If we don't, we'll just see what happens. So when we distribute that 4, again, I'm going to carry this limit notation with us the whole time. When we distribute the 4, well, 4x divided by 4 is just x. And then when I multiply 4 by 1/2, that's just 2. So our numerator becomes x minus 2. And now you could see why I said hold off on distributing the 4 in the denominator, because we would just have to factor it out again. So now we can, again, cancel, quote unquote, factors of x minus 2. We're left with a 1 on top. And so our limit value, there's no more x's. There's nothing left to plug in. Our limit value is 1/4. Now you might be looking for patterns, and you might notice that all 3 of these examples had an answer of 1/4 or negative 1/4. That's just a coincidence. That's just how it worked out when we wrote the spiral. Don't read into that too much. That is not on purpose. So, all right, we said this was an example of clearing complex fractions. All right, so what I would like you to do is I would like you to pause the video and try these next 3 examples using the 3 strategies we just tried on your own. And then when you're ready, resume the video and we will check those. Okay, hopefully you tried those 3 on your own. For this 4th example, I'm going to star these. I kind of wish they were numbered. This next example, again, this is where we would multiply by the conjugate. So if I look at my denominator, the square root of x minus 3, that's kind of my clue that if I multiply the numerator and the denominator by the square root of x plus 3, the conjugate of the square root of x minus 3, that's going to allow me to get rid of the radical in the denominator. And sure, it's going to create a radical expression in the numerator, but our goal is to get this algebraic manipulation where we have a common factor in the numerator and the denominator. So we get this common factor of x minus 9, and that is what we are. Again, I hate to say this word, but I know you know what I mean. We are canceling. So we don't eliminate the whole until we eliminate the factor of x minus 9 from the denominator, because x equals 9 was causing the whole. Or rather, plugging a 9 into x minus 9 was giving us that 0 over 0. So we've gotten rid of the 0 over 0 at 9. We have a new function that behaves like our original function without a whole, and so that limit is 6. Okay, this second to last example, when I look at this looks like something I can factor. And really, we're just factoring out a greatest common factor in the denominator. So it's not like trinomial factoring like the first example. So we could just take our 3x squared minus 12x and factor out a GCF of 3x, and we're left with the remaining factor of x minus 4 in parentheses. And so again, when we notice now that we have common factors in the numerator and the denominator, that's what we are canceling out to remove the whole discontinuity. So our new function, 1 over 3x, is not the same as our original function. Our original function had a hole in it at x equals 4. Our new function does not. And when we substitute in the 4, we get 1 over 12, 1/12. All right, last example. Also, if you want to see this, like if you want to try graphing this and comparing them, you could plot those both in Desmos and notice that they are pretty much the same graph. For you to see that there's a hole, you would have to click on the function where x is equal to 4 in Desmos. We could look at that in class. All right, finally, that last example was clearing a complex fraction. So again, we said the most efficient way to do this is to multiply the top and bottom, the numerator and denominator of our big fraction, quote unquote, by the least common multiple of those little denominators. So the least common multiple of 7 in x is 7x. And when we distribute that to the top, we get 7x squared over 7, which just becomes x squared. And we get 49x divided by x, which becomes 49. There's subtraction between those two terms. And again, on bottom, I would not distribute the 7x. Who knows? Maybe later we need to, but I'm going to leave it. But then I realize I still have to factor. Nothing cancels out from this form, but I might notice my numerator is a difference of squares. So that's going to factor to x plus 7 times x minus 7. We can eliminate our discontinuity right there. We get a function x plus 7 over 7x. And when we plug in our 7, that's going to reduce to 2/7. All right, so those are the 3 main algebraic manipulations that we can do to remove a whole discontinuity. There's one other thing that we're going to learn today, and then in Unit 2, we'll actually learn one more thing we could do to evaluate these limits. All right, so there are 2 fundamental trig limits that we really just should memorize. And I want it to be really clear that that it's not just the limit as x approaches anything of sine of x over x equals 1. It has to be specifically the limit as x approaches 0. But I want to also point out that often in math, when we see a rule like this, it's really broad. So I could actually look at this trig limit property, and I could think about, what if I had instead the sine of like 3x, and I was dividing that by 3x, and I'm looking for where 3x approaches 0. Well, this is also 1. So as long as these 3 expressions match, they're the same, and it's approaching 0, so it's the limit as this approaches 0, that's when we could apply this identity or this limit. So more generally, sometimes I know it's a little silly, but I like to think of it in more general terms, that if I had like the sign of a smiley face divided by a smiley face, and I'm looking for the limit as the smiley face approaches 0, that's going to be 1. And that smiley face can be any expression. And the same is true with this other limit. The first one is probably going to be something that comes up more often. So I would memorize them both, but our first trig limit here, we're going to see more often. Okay, so when we look at this next example, right off the bat, I'm like, wait a minute, it doesn't look like either of those. What's going on? So we might have to do some manipulation with cosecant to get it to look like one of these two forms. And when I was a student, that was always tough for me. That was the hardest thing for me to understand when I was learning trig. And what I could tell you, like as a math teacher now, what I wish I knew as a student is sometimes you just have to play around with it a little bit and try some different things until you get something that works out. It might not be the first thing you try. So I remember that cosecant of x, that I could think of that as the reciprocal to the sine of x. So cosecant of x could be written as 1 over sine of x. Already I'm thinking maybe that's helpful, because I notice that this would kind of start looking like what we have over here, but it's kind of backwards. So I'm going to trust my gut and try it this way. So the limit as x approaches 0 of x times 1 over sine of x is the same as just saying the limit as x approaches 0 of x over sine of x. All right, so I might notice that that is the reciprocal of what is in that box. So when we think about reciprocals, we could think of like a over b and b over a are reciprocals. We could think of flipping a fraction, but I could also write the reciprocal of a over b as 1 divided by a over b. And I think thinking about it that way is going to be the most helpful thing here. So I could think of this as the limit as x approaches 0 of 1 over the reciprocal of this, which would be sine of x over x. So now when I plug this in, I'm going to end up getting our limit is 1 over 1, and that is just 1. And if you go back a couple pages in our text, in our spiral, back to page 2, you will see kind of at the top of page 2 before the example with the graph, a couple properties of limits. So, you know what, as I'm saying that, that's actually continuity. We might need to go a little bit further back, but we can, sorry, I'm looking back through the text now. We can absolutely use that property to evaluate this limit. I'll look up what page it's on in class. All right, let's look at this next example. We have the limit as x approaches 0 of tan of x over x. And again, what jumps out to me is that does not initially look like anything we're working with right now. So that means that we need to find a way to rewrite this. And I know I could think of tangent as 1 over cotangent, like that reciprocal identity, but that doesn't help me either. So maybe instead I want to think of tangent of x as the sine of x divided by the cosine of x. That reciprocal identity might be more helpful. All right, so if I rewrite this, I'm evaluating the limit as x approaches 0 of, and instead of writing this all over x, I'm going to think of this as like tangent of x times 1 over x to start with. So I'm going to think of this as the sine of x over the cosine of x times 1 over x. All right, this is starting to look closer to that first trig limit in our box. So I could think of this as the limit as x approaches 0. And when I have multiplication, I could just swap my factors in the denominator. So I could think of this as sine of x over x times 1 over the cosine of x. And now I know that when I plug in a 0, this expression, that's going to go to 1. Like that function is going to approach 1 as x approaches 0. So I really now just need to consider what happens to the 1 over cosine of x. All right, so we have 1 times 1 over the cosine of 0. And again, I need to remember on my unit circle that if I'm on my unit circle out here at 0 radians, that is the ordered pair 1, 0, and that cosine is our x value, sine our y value on the unit circle. So this just becomes 1 times 1, which is 1. All right, so the value of our limit is 1. All right, let's look at one more together, and then I'm going to encourage you to try a few on your own. So at the top of page 6, something I notice immediately, or something that jumps out to me immediately, is that first expression where I'm evaluating the limit as x approaches 0 of sine of 3x over x looks an awful lot like that first trig limit in the box. So what I need to do, though, is I need to think about that 3, because I don't just have the sine of x, I have the sine of 3x. So remember, the parentheses around this are implied. 3x is the argument of the sine function. I can't get rid of that 3. But what I can do is I can create a 3 in my denominator. So I can rewrite this and think of this as the limit as, and I'm going to say as 3x approaches 0. And I'm going to take my function here and I'm going to multiply the top and the bottom by 3. And again, the reason I'm doing that is to make this denominator, 3x, be the same as our input to our sine function. So I get 3 times the sine of 3x as my numerator over 3x as my denominator. And I could also think of this as, I could pull like this 3 out front. I could think of this as 3 times the limit as 3x approaches 0 of the sine of 3x over 3x. And that is just going to become 3 times 1. Now, I want to note when I said that we could pull this 3 out front, that's because it's a constant multiplier. You can't do that if there's like addition or if it's a function of x itself. Or you could just leave it right here and you still get 3 times 1. So it doesn't really matter because this is the stuff that's going to 1. All right, I would love for you to pause the video and try these last 3 on your own. And I know some of them are tricky. Just do your best and then resume the video in a moment to check. All right, as we look at the top right example on page 6, there's actually kind of 2 ways that we could consider this one. So you might have thought of 1 minus cosine squared x. You might have thought of that as a difference of squares, and we could actually factor that just like a difference of squares. And if we do that, we'll notice that this part of our limit expression, that's going to relate back to that second trig limit that we wanted to learn on the previous page, that the limit as x approaches 0 of 1 minus cosine of x over x equals 0. So if I were to substitute a 0 there, I know like this part of my limit is going to go to 0. When I plug in a 0 for x over here, I get 1 plus the cosine of 0. The cosine of 0 is 1. So this becomes 1 plus 1, which is 2. So if I think about multiplying those two numbers, I get 0 times 2. Also, earlier when I was referring to properties of limits, I think I said the wrong page number. That's actually not until the top of page 9, which is in a subsequent section, but if you want to look at the top of page 9 in your spiral, you'll see some properties of limits there that might justify some of the way that we're thinking about these. So we'll dig a little deeper into that in a couple lessons. All right, this bottom left example, again, this looks like something that we can manipulate to look like our other trig limit that we said we wanted to memorize. So the first thing that I would have you recall is that we can't do anything about this 2, but I could think of this as like the limit as x approaches 0. I could think of this as a 1/3 times the sine of 2x over x. So I'm just kind of pulling that 3 from the denominator out separately, calling that a 1/3. Now, if my goal is to make this a 2, I can multiply by 2 on the bottom, which means I have to multiply by 2 on the top. And this is now the limit as 2x approaches 0. So now if I evaluate this limit, I have like 2/3 times the sine of 2x over 2x, and that just becomes 2/3 times 1. So 2/3 is our final answer there. All right, lastly, I got to back up and say in these last 2 examples, I did not model something well for you. And what I should have reiterated, I'm catching myself now, is that the first thing we should always do is plug in the function value. I'm just on a roll because I know what I want to say about these problems. So just to be clear, when we plug in 0 for x in these examples, we do get 0 over 0. 1 minus the cosine of 0 squared is 1 minus 1. Down here, when I plug in 0 for x, I do get sine of 0, which is 0 over 3 times 0, which is 0. So where this could get tricky is if you didn't do that on this last example, you might have made a mistake here. When I plug this in, the sine of pi over 2, well, that's 1. That's not 0 at all. And our denominator is just pi over 2. So there is no hole here. This is a place where this function is continuous. So we get 1 divided by pi over 2. And again, if I want to clear that fraction in my denominator, I'm just going to multiply my numerator and denominator by 2, and I get 2 over pi. So those 2's become a 1. Okay, the final example, or 2 final examples that we're going to look at, come back to this idea about continuity. So remember in our first lesson, we talked about this previously in this lesson, the definition of continuity, the DOC, the definition of continuity tells us that if a function's continuous, its limit must exist. So like the limit of, I'm going to say f of x as x approaches a from the left has to equal the limit of f of x as x approaches a from the right. So that's just the definition of a limit. That tells us the limit exists, but the limit must also equal the function value. So f of a, whatever a is. So this is the definition of continuity that I believe is on page 2 of our spiral. So in this example, if we're asked to find the value of b such that g of x is continuous for all real numbers, I'm going to point out that when we find a value of b, that means that b is a constant. Okay, so for this function to be continuous for all real numbers, the thing that will need to be true is that there is not a jump at x equals 3, the boundary of our piecewise, because otherwise these two pieces, there's no denominator. So there's no chance of us having a whole or a vertical asymptote. So I just need to make sure there's also not a jump. So I'm going to consider x equals 3. And what we need to be true is we need the limit as x approaches 3 from the left of g of x to equal the limit as x approaches 3 from the right of g of x. And because of where this inequality is on the piecewise, on the boundary, we already know this last part's true, that that's going to be equal to g of 3. But I don't think it would hurt for us to write each one out. All right, so as I evaluate the limit of g as x approaches 3 from the left-hand side, I'm using the top piece of my piecewise because from the left of 3 is numbers less than 3, and I get 3 squared plus b times 3, which is just 9 plus 3b. When we evaluate the limit from the right, so as we approach 3 from the right on the x-axis, I know I'm using the bottom piece of my piecewise. That just becomes 4 times 3 minus b, or 12 minus b. And that's also the value of g of 3, because our function value, I would plug in the 3 to the bottom piece. So that's also 12 minus b. So we end up getting a system of equations that in order for, we already know these two things are equivalent. In order for these two pieces to be true, it must be the case that 9 plus 3b is equal to 12 minus b. So the limit from the left equals the limit from the right, which is also equal to g of 3. And I said a system of equations. I'm sorry, that's just one equation. We're going to see this come up later where we actually get a system. All right, so if I'm solving this equation, I could subtract 9 from both sides. I could add b to both sides. I could divide both sides by 4. We get that b is equal to 3/4. All right, this last example, very similar. Find the value of k such that f of x is continuous at x equals 0. And we said really what we're worried about here isn't so much a jump discontinuity, but this is how we could possibly have a hole given a piecewise defined function. So again, we want to evaluate the limit of f as x approaches 0. And if I'm approaching 0 from the left or the right on my number line, if I'm coming at 0 from the left, those are all values less than 0. If I'm approaching 0 from the right, those are values greater than 0, but generally all of those are values where x does not equal 0. So if I think about my number line, if I shade in both directions and have an open circle at 0, that's just represented with x does not equal 0. All that to say is that we do not have to do two one-sided limits. We can just find the limit using that top piece. So again, I've got the sine of 2x over x, the limit as x approaches 0. And that is going to, again, be like that trig limit that we saw on the previous page. So in order for me to make this a 2x, I need a 2 there. All right, so now the limit of 2x well, we know that this piece goes to 1. So we just get 2 times 1, which is 2. All right, so we've established that the limit is 2. So that must mean that the function value is 2. So if I know that f of 0 is k, and I need f of 0 to be equal to 2 for our function to be continuous at 0, well, that means that k is equal to 2.